All right, I'm back for another example on section 6.2, doing hypothesis test for one mean. We have a question here. It says you wish to test the following claim at a significance level of alpha equals 0.005, and we have the null hypothesis that mu is 77.1. Okay, so a couple things so far. Alpha, 0.005, and then mu, which I sort of forgot to write down last time. Kind of an important player here. And then we're given our null and alternate hypothesis here. So the important thing to gather, we are dealing with a right-tailed test. So when I draw my sweet little picture, I'm going to have a curve looking for the area of the right. So you believe the population is normally distributed, but do not know the standard deviation. You obtain a sample size, n equals 120, with a mean, that's x bar, 78.8, and a standard deviation of 7.1. Again, kind of translating these into the language that we are using in our text. So I have enough information right here, kind of, to draw myself a little distribution and a picture. Now, last time I kind of struggled through getting these guys on here. So our mean, 77.1, is here. And then 78.8 is going to be somewhere over here. Anyway, a little easier if I use the stylus, but I know not everybody has that. So here we go. This is our p-value, that little area to the right, because we are right-tailed. So now to figure out our test statistic, we need the standard error. And our standard error from our formula sheet is S divided by the square root of n. And again, that's the sample standard deviation divided by the square root of the sample size. And then we can use that to find our test stat by taking the difference. We're going to do x bar minus mu. The claim value always goes last, and you got to group those and then divide by the standard error. And this gives us our test statistic. Now we are looking for this is a right-tailed test, and so I've got the p-value. If I go here, I actually have a t-distribution right tail that I can use. And notice here it says x in degrees freedom. So I can tap here x and the degrees of freedom. I didn't make them yet, but it is n minus 1. So I can click on n, do minus 1, and you'll notice here there's nothing more to do. The t-distribution right tail just has this stuff for us. Now, I maybe should have added the degrees of freedom here. If I want to, I can. 120 minus 1, taking that n minus 1. Sometimes I make the degrees of freedom there, sometimes not. So this is a new function. If we were to do this the old school way, when we're looking for the area to the right, we do 1 minus, and notice if I go t-dist, I have the t.dist, and then I can put in my test statistic, my degrees of freedom, and then true. And I'm showing you this way because sometimes it's nice to just keep the process the same. So this is sort of the similar thoughts as to how we were doing with the normal distribution. The t-distribution allows us to do a t-dist right tail. So now punching in some answers, making a decision, and coming to a conclusion here. Our test statistic to 3 decimal places. So 6, 2, and then another 2 followed by a 9 is going to be 623, 2.623. And then our p-value to 4 decimal places, I got 0.0049 followed by a 3. If this 9 was followed by something larger, it might round up and we might get 0.0050. That's okay. Now we make a comparison of this to this, which is actually quite close here. Our p-value is less than alpha, so we will reject the null hypothesis. And there we go. All right. Now here is another two-tailed one. I want to get to this one if I have time. Because notice a little different. We've got a null, an alternate hypothesis, and an alpha. So I'm going to take those in. Alpha equals 0.10. And mu is 77.7, and this is a left-tailed test. And we have a data set. So I'm going to grab our data set, take it over here. When I have a data set, oftentimes I like to paste it special. Occasionally, you'll get a number that doesn't quite come over right. So now we have a data set. We are missing some information from what we used to have, so we have to kind of gather that. So you can use the count function, or you can just look here. N equals 6. Now we need to figure out what our x bar is the average, and we grab our data set. We also need the sample standard deviation, and again, standard deviation, this is a sample. We're trying to use a sample to make some inferences about our population. Had some questions about why it's not just a population. So that's that. All right, what else do we need to figure out? We could use the degrees of freedom. That's n minus 1. We are dealing with a small sample size here. And standard error is going to be important for figuring out our test statistic. So our standard error is the sample standard deviation divided by the square root of n. And just clicking around, letting these guys do work. Now our test statistic. I haven't drawn the picture yet here. My mean here, 69.48 x bar, and mu here. So if I try to make a little picture, and maybe I'll just do it down here. Oh boy, that's the worst distribution. But I'm not going to be too worried about that side. 77.1 is here. And then x bar, 69.5, we'll say, just to keep it easy. Again, numbers here. And this was left-tailed, so my p-value is this stuff. Okay. A little rough there. So our test stat is x bar minus mu over our standard error trying to grab the right stuff there. 3 decimal places, negative 5.4175, so that's going to be an 8. And then our p-value, p-value equals t-dist. I can just use a t-dist. I've got the test statistic here, the degrees of freedom, I actually wrote it up here, and then true just gets me the area to the left. Again, kind of functioning really similarly to how our normal distribution did last time. And by last time, I mean in the previous section. So 0.00145 is going to go to 0.0015 here for our p-value. And that kind of makes sense because we're like more than 5 standard deviations to the left. And we have some basics right on how these work. So comparing this to this is definitely less than that, which means that we're going to reject the null hypothesis, and there is enough evidence to support the alternate hypothesis that the mean is less than 77.1. So again, a couple examples worked through, and you're kind of seeing the process. We have some new options here for the t-distribution. Sometimes it's worth it just to keep it like the old school way, and sometimes it's nice to use the new tools. You got to make the decision on what works best for you. Let me know if you have any questions.